Yes,
Yes,
sir.
sir.
Oh, ask them. Oh, I couldn't find the link. I just meet now. It's all 5. It's 5. Okay, let me share it. Okay, so I didn't share it. I was having some problem. Share हो गया. It's all right. Fine. Can you hear me? Can you see the screen?
Yes,
Hello?
sir.
Yes, sir. Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Start. I think my laptop is giving some problems. It is okay. So let us start with continuity. Okay. So I'm just recalling that when you have a function and that, suppose you have this. And suppose x belongs to R. Then f is continuous at means what? Means, look, given epsilon. That means you choose epsilon, any epsilon, positive epsilon. There exists delta greater than 0. Delta depends on epsilon, such that x minus x prime less than delta implies this. Less than epsilon. So now instead of this, if you have a metric space, function between two metric spaces. Now look. So you have metric space, different metric space in that. They are not the same thing. Y row, okay. Then okay, that look what I'm doing. X belongs to x, then f is continuous, means here distance. So it will be d x prime less than delta implies rho fx prime less than delta epsilon. Okay, so this is just actually what happens between the real lines and the continuity on the real lines that you copy here. Basically distance d here, rho here. Here just a notational warning that xy usually small y you use as an element of y and small x usually is element of big X. That's why I'm taking x prime, not y here. Okay, that you should follow that. Okay, now I have shown that under next definition, if so, you have a metric space, you have a function between two metric spaces, and if f is continuous, if f is continuous at each point x, then F is called continuous on X, or we simply say that F is continuous, or simply say that F is continuous. Look here, the terminology F is continuous means F is continuous on whole X, that means each point of X. Otherwise, if you have some continuity at point, some point, then you'll have to say that F is continuous at X. Okay. Now, this is called actually, some people call it global continuity. That means continuity on the whole thing. Whereas, if you just take a point, then it is called a local continuity. Local continuity. Okay, right. Now, I have given the examples on that. Okay, that you should read at that. Okay, let me tell you that. First of all, here, page 104. Go there. Okay. First, the simplest thing you can start, you could take identity map. That is it, that between the same metric space, range and domain, they are same. X going to X. Here, obviously, it is continuous at each point. Actually, you can take for each point delta equal to epsilon. Given epsilon, you choose delta equal to epsilon. Okay. Now the next thing, look, nice functions should be continuous. That we are checking. That example one, that identity map, but make sure this is the same metric, not different metric. About different metric, you may not know what will be the outcome. Okay, this is example one. Example two, we'll see the constant function. Constant function like you did, suppose xt is a function. Another metric space. Constant function means here you pick up a point that why not, and suppose everybody is going to this, suppose fx equal to why not for all x belongs to x. This is called the constant function. That is, as you did on the real analysis, real case, then it should be continuous. Okay, this is continuous. Okay, then I asked what will be given epsilon, what will be your delta? Given epsilon greater than 0, what will be your delta? What is your delta? You can choose. Okay. Well, here you see. Given a, huh? What delta? Any delta? Huh?
For whole x in x, sir.
Any delta will work. Look, rho fx, fx prime. It's a constant function. So fx is also y naught. This is also y naught. So this is 0 less than epsilon. So it doesn't matter what x prime distance. So that dx x prime less than delta always imply, that means you can choose any positive delta. You understand? Here you can choose any positive delta. Okay. And now look, example 3. Look, even if you change the domain codomain, that how it gets affected. Look, if you take this function, but here you give the discrete metric. Take the identity function. Just now I was telling that identity function need not be continuous. Look, here I am giving the identity function, but f is not continuous. But f is not continuous at any point. You should check Okay, I said check that. Okay, this is easy to check. But you see that if I change the domain and codomain the side, that means if I take this, now we call it G. Joe, it is identity function. But I'm calling it G because I have changed. Domain is here, codomain. Range was domain here, a domain was range here. This is continuous at each point. That you should check that why it will be continuous in that. It is not continuous here. It is continuous at here each point. Here you should, I should tell you, remind you that when you talk about a function, domain of a function is very important. You need to mention what is domain, what is range. They are very important. Just if you give some formula you did in the undergraduate, some calculus, some f equal to this, that is not enough. That you need to say what is your domain and what is your range. Look here, the example is there, that how it is important. Okay, right? Okay, so make sure that you understand that. Next, example 4, I put a star here. Now look here, I have given actually the definition of an isometry. It may happen that you have this isometry means, look here, suppose you have it rho fx prime equal to dxx prime for all pair. Okay, then f is called an isometry. Look, identity map from xd to xd. Identity map, that is a special case of that isometry. Now look, isometry by definition, you look, if you take delta equal to epsilon, it will work. So it will be continuous. Okay. And also see that isometry by definition, it has to be one-to-one, because if you have fx equal to fx prime, then this will be 0. So this will be 0, so x will be x equal to x prime. And isometry is always one-to-one. But it need not be onto. But be careful. But it need not be onto. That's why if an isometry is onto, we emphasize onto isometry. Simplest example is here. Look, I give this from an usual metric, which is actually discrete metric here, to this n itself. Take this n going to n plus 1. Look, this is an isometry, but this is not onto because 1 doesn't have a preimage. Okay, 1 doesn't have a preimage, so this is not onto, but it is isometry. Okay, here usually some books they ask that why I'm saying that. Look, if you from R is equal to R square, to take the same thing, you can take the inclusion. That means x going to x0 basically. So this is an isometry, but it is not onto. Okay, it is not onto. Okay, you should check why it is not onto. But okay, but I am saying this isometry may not be onto, but the question is, does there exist another map which will be an onto isometry? So I have given to C But look, they are isometric to each other. See, with this, if I take this map, the natural map, I will give this iota. This will be an isometry onto isometry. Composition of two isometry will be an isometry. Okay, so here I am asking, there is no onto isometry between them. Similarly, here in the note I said so that no onto isometry. Actually, so does there exist an onto isometric from R to C? Okay, in general, I'm giving this question later on that. Okay, so let me explain that. I will problem the author. Okay, so I think it is somewhere in the node of isometry. I will teach you separately, but since I have talked about isometry, you should think it's the geometry and that. Look, suppose you have, an onto isometry. Okay, and A is a non-empty subset of. This is the next note will come. But still, I am since talking about isometry, I can say that. I can discuss a little bit. Now look, so you can show that F restricted to A. This, of course, you are taking this FA row. Okay. But it is not only that, that you are taking FA. So obviously this is onto. Okay. And this is also isometry. Okay. That if you have an isometry here, this will be isometry. So particularly, it's a bijection. So that means, as said, the size of FA. Now look, cardinality of FA will be same as cardinality of A. Okay. Why I am doing this? This you can linear prove, and from here you can prove there cannot be an isometry from R to C. Look, when you go R to C, look, all you have to check. Suppose since this is an onto isometry, so yeah, okay, let me write that. So this is done. Okay, so let me write this. Okay, so okay, now look, okay. Suppose you pick up a point x0 belongs to x, and y naught you call fx naught. Okay. And you pick up any number r greater than 0. Suppose you take a equal to x belongs to x such that d, this is actually called circle, dxx naught r. Okay, all those points with distance r, and b you take in y such that rho y naught equal to r. Okay, this you do it. Now we can show that I've seen isometry that this map we will go to this, that means FA will be equal to B. Show that. Actually, easiest way to show it is just show that FA is contained in B and B is contained in FA. That's the way you prove it. Okay, right? So that B, this you prove. Now if you prove it, since F is an onto isometry, F is a bijection. So here it is also one-to-one correspondence. That means cardinality of A will be cardinality of FA, but FA is the cardinality of B. That means what you are getting? That means in the circle, the points, number of points, basically you can say loosely, will be same as number of points here. Did you get it? Okay. I am doing some geometry. Now look, if you have an, now you can use this. Suppose you assume complex plane. Suppose you have a map. Suppose you have onto isometry. Okay. Then you can choose R equal to 1 also, whatever you choose. Okay. Then what will happen? Then here, if you take, you can pick up 0 here. You do not know where 0 is here. But now look, then A x belongs to R such that norm of x equal to 1, supposing to it. And here B, we are taking that x, y, z, you are taking z belongs to C such that, okay, got it. Look, if it is an onto isometry, there the size should be same actually, right? That we have initial proved and that. Okay, actually Z belongs to C, you should not take this. Wait a minute. Here, since I do not know where F0 will go, I will take this. Let me tell you that. We will take B equal to, I have taken 0 here center. You take sorry. Z belongs to C such that Z, its image F0, I do not know where F0 will go, equal to 1. So here is the, so in the interval, that means what you are having about 0. This will be point only -1, 1, 2 points you get. Whereas here it will be circle, that if your image, you will get basically, if your center is F0, then you will get all these points with this. But this is infinite set. This is only finite 2 points. So they cannot have the same cardinality. There is a contradiction. That's why no onto isometry. Okay, right? So I have given you the Jan thing here. We'll come back on that. You think about it. There is no onto isometry from R to C. Okay. Now, characterization of the continuity. Fine. The thing is that you have definition of continuity, but often we do not check continuity like going point by point delta epsilon. So here in theorem, you see that I have given 5 equivalent conditions. Okay. That now remember that when I had that I discussed last time, it is written before. Suppose x belongs to x. Okay, f is continuous at x. It means given epsilon greater than 0, there exists delta greater than 0 such that dx x prime less than delta implies rho fx prime less than epsilon. But I told you given epsilon means actually you are having a ball, open ball centered at fx. Look, this means fx prime belongs to B rho. This I indicate is the open ball in y. Fx epsilon. This is the meaning of this. And whereas the meaning of this is B T X delta X prime belongs to B delta implies this. This is the meaning of this in terms of the balls. So that given epsilon greater than 0 means you are choosing any ball, any neighborhood of fx in y. Then you are getting a neighborhood of x here such that entire neighborhood is contained in this. This means actually what? This means f of bd x delta is contained in B rho fx epsilon. Got it? So this is the important thing you'll have to understand. That means given a neighborhood of fx prime, I will get a neighborhood of x such that the image of the neighborhood will be entirely contained in the neighborhood of fx. This is important. Okay. Now look, I have given 5 conditions. That first look at A, and so you are having a function xt y rho. I am saying the following are equivalent. Here I am considering the global continuity on whole x. I say the following are equivalent. That first A, f is continuous on x. I am going one by one. That is f is continuous. B. Look here, often we use it. F inverse u is open in xt whenever y is open, u is open, whenever u is open in y row. Okay. Look here, you can read the note I'm telling you. So when you want to prove that f inverse u is open, that means the only thing you'll have to show, that is the only tool basically you have. You have only the definition basically. You have to show each point is interior point. Okay. So take any point here. I'll have to show it is an interior point. That means I'll have to show there is a ball around x which is entirely contained inside f inverse u. Now x inverse fu implies fx belongs to u. Now look, I'll have to go to y because this is the tool I have. This is the fact I have. But fx belongs to u and u is open in y. This is open in y. That means each point of u is an interior point. So that by this, okay, fx belongs to u. Now it implies there exists that I am taking epsilon, you could take r also, such that b rho fx epsilon is contained in u. Okay. But this means what? Look, you are done basically. Okay. But look, I have given f is continuous on x. So particularly f is continuous at x. That you'll have to use. But since f is continuous at x, I have this. So there exists the ball around this BD x delta f will be contained in this. But this means what? To go for this. That means BD x delta is f inverse b rho fx epsilon, right? Going for the pre-image, but this is contained in u, so that this will be contained in f inverse u. But x was here, so forget about this fellow. That means you are getting this. That exactly I needed to show that each point of f inverse u is an interior point. so that F inverse U is open. Often we check that inverse image of an open set is open by this. Since I have to complete the circle, I have not done it. I have proved A implies B. So I have proved A implies B. Okay. Now B implies C. Well, just to show that I'm saying whenever xn goes to x, fxn goes to fx. That you'll have to prove. Okay. Actually, I am saying this you have. Now look, it's easy to prove that. Basically, you'll have to show each neighborhood of fx contains a tail of the sequence. So you take this. Take any neighborhood of x, or you take epsilon. This will have to contain a tail of this sequence. Fine. But look, my condition by B, this is open in X, it is XD. But look, F inverse Fx is Fx is here. So when you are taking preimage, that means X belongs here. Got it? Okay, because X belongs here by definition of the preimage. But this is open in X, so that there exists delta. This is open. Okay. Here, by the definition of open, there exists delta greater than 0, such that but now see, link with this here. This contains a tail of the sequence. That means xn belongs to bd x delta for all n greater than equal to n naught. Some n naught exists. Okay, there exists n naught, such that for all n naught xn belongs to, but xn belongs to here. That means xn will belong here for all n greater than equal to. If xn belongs here, that means fxn by definition of preimage, fxn belongs to b rho fx epsilon. But that is true for all n greater than equal to n naught. That exactly needed to show. Okay, that it contains a tail of the sequence. I started with this. Okay, so you get this P implies C. Okay. Actually, read C carefully. It is not only for one sequence xn converging to a point x. It is for any sequence that you should careful. For any sequence, you should have this condition. Just not for one sequence. Okay. Right. Now, C implies D. Look, in the entire proof of this result, this is bit tricky. Okay, this is bit tricky. So that I am explaining this, and still you should read the proof on your own to understand what is there. Okay. Oh, not C implies D. C implies D is easy. Okay. Not D implies this is easy. This I am leaving it to you. This you will use sequential characterization of closure point. That is very simple. Okay. Fa but it is important, I am telling you where. Yes, sequential characterization of closure points you will be using in both directions. Remember that X belongs to a bar if and only if there exists a sequence xn in A such that xn converges to X. Good thing about the proof of this, we will be using the both direction in here by sequential characterization of closure point. Okay. Look, having again using the by using the sequential characterization of closure point we get. We are using in both direction. Okay. Now D implies E. This is a bit tricky. Let me tell you. Okay. Right here. Look here. look, FA bar, you are having FA bar for all subset of Ax. You are having this condition. And you'll have to show that this is inverse image of a closed set is closed. Compare with B. Actually, since closed sets and open sets are dual, so at least you can prove, look, immediately. Without knowing this will be always, you can prove it, that since closed set, open set are dual and that. Look, here you should understand, like I'm just talking about beam and equivalence of En. Look, here you should see that. Suppose X minus F inverse C. C is a subset of Y. This is nothing but, look, X is F inverse Y. Complement minus F inverse C. So this is, you can write F inverse Y minus C. Got it? Okay. Now you see, if you assume C is closed, now look, suppose B is, you have B, then you have to prove E. Okay, fine, you prove, you assume C is closed. C is closed means Y minus C is open. So by B, this is open, but this is open means this is open. That means F inverse C is closed. Okay, so this way, this is true immediately. You will have to just use this thing and the definition of closed set. Okay. Now look, this condition, let me write it here. D is this. Don't, first thing, don't confuse here. Here closure is first and here closure in the over the whole thing. That means here F closure of A is contained in closure of Fa. So here F comes first. Look, but here not equal. Here I am saying this is contained. That's why you'll have to be careful. If it is equal, then you didn't need to bother. But that's why, but here it is only subset. So here F of closure, that you are interchanging, but it is contained. That's why you should remember that. Okay. Now look what I did. Okay. So that I will have to prove this is D, and you will have to prove E. To prove E, that means you'll have to show that F inverse C is closed in X. That means XD whenever C is closed in Y. Okay, right. So I have taken. Now that you'll have to show. Now since C is closed, C equal to C bar, since C is closed, that I have seen. Now apply D on this. Now this is the vital trick. You take A equal to this and plug here. Okay, right? But you should follow one thing, that A equal to F inverse C, that I said that implies FA is contained in so if you remember this, then you can do it immediately. It's not a problem because but But so that I am not completing it, that you should complete. But here you should careful. A equal to F inverse C means Fa is contained in C. Look, I may not recover the whole C. Reason is if F is not onto, understand? If F is not onto, then it may be a proper subset of this. Okay. So don't write A equal to F inverse C equal to Fa equal to C. It will be null contained in this. Only if F is onto, then Fa will be equal to C. Okay. So that you need to know this trick. Okay. Then it's fine. Because look, I want to show that the F inverse C is closed. I have taken this. That means I'll have to show A bar equal to A. But A is always contained in A bar. So that I need to only show this. This only I need to show. Okay, right. Now E implies A. Now look, if you, I am just telling you that because E implies A, you should prove that. I am not going to prove it. Look, I have said actually A and B, they are equivalent. You can prove it yourself. So when I say actually E implies A, I am proving it. You should look at the proof. E implies A. I am proving F is continuous on X. I am proving F is actually continuous at each X. So you look at the proof. Actually E implies A. We actually, the trick we prove this actually. That actually we prove this. That you should look. Okay. Right. Make sure that you read the entire proof, you understand. Now look, here you have 5 equivalent conditions. Okay, wait a minute. 5 equivalent conditions. Then you may ask why we are doing these all these equivalent conditions. Thing is that when you go for application, that to check, look, that means, look, why these equivalent conditions are important. Suppose you have given a function between two matrix spaces. Your first query should be, is F continuous? Because if F is continuous, you can do many things. If F is not continuous, you may not be able to do many things. So this is your should be first query. But then how to check? Look, there is no hard and first rule, fixed rule. Here you have 5, basically F is continuous on X, that means you have 4 more equivalent conditions. Depending on your question, depending on your problem, you maybe use one of them to see that which is easier to do it. Often condition C is, first you should try actually condition C. That condition C gives a sequential characterization of continuity. Okay, like already you did sequential characterization of closure points, sequential characterization of accumulation point. Here I am giving you sequential characterization of continuity, sequential characterization of continuity. Okay, this is very powerful. First you should try it, but sometimes you get easier things that B or E. But here about D, let me give you an example of this. D. Look here, first of all, suppose you have a function between this. Now suppose A is dense in X. Suppose you have it. And then look, by this, and suppose you have given F is continuous. Okay. Then now look, by this, Fa bar contained in Fa bar. But obviously here everything you are working inside Y, so this is in Y. But Fa bar, A bar equal to X, so Fx. Okay, right? So fx we are getting contained in y. Well, sorry, okay. Fa bar is this. Fx we are contained in Fa bar equal to x. Okay, right. A bar equal to x. The fx equal to this. Okay. Now, so what does it mean that? Okay, that fx we are getting fa bar. Okay. Well, first just take this is onto. For later on, see this is onto is not required actually much, but take onto. Then onto means this will be y. That is fa bar equal to y. That means what you are getting. If you have an onto continuous map, if A is dense in X, then its image is dense in Y. Its image is dense in Y. Then it says, what's great about it? Look, now particularly if X is separable, not all subset will be countable dense set. Now then there exists a countable dense set A. So there exists a countable dense subset A of X. But you can easily prove if A is countable, its cardinality of FA, you need axiom of choice. Will be always less than equal to cardinality of A. That means through map, the size of a set cannot be bigger. It will be either remain same, like if F is 1 to 1 correspondence, then it will be same, or it will be less. So if A is countable, then FA will be countable. FA will be countable. That means if you have a countable dense subset here, then you will have a FA will be countable dense subset of Y. That means what you are getting. That means if X is separable, then Y will be also separable. Got it? So now look what I have got actually. Okay, first let's see continuous image. Continuous image, the term. If you have xt y rho is a function continuous onto, that is y equal to fx, then y is called a continuous image of, y is called a continuous image, continuous image of x. Look what result I have proved. A continuous, this I have proved actually, a continuous image of a separable metric space is again separable. Here I got a result. Also look, if I apply D, it is immediate. You could apply other things. It's not difficult than that. You could do it, but immediate. Okay, so it depends on your case. Okay, right? That which one you will handle, which one will you use. Okay, fine. So that look, if you look at the proof carefully, okay. I said actually condition C of theorem 6.11 can be used to give the following sequential characterization of continuity of F at a given point X. The precise statement follows. Page 107, you see that. Suppose I do not use global continuity, I use local continuity. So let F be a function between two metric spaces and X belongs to it. Then the following are equivalent. F is continuous at X And whenever xn goes to x in xd, then fxn goes to fx in y. That exactly the proof says. Okay, but what I want to say that you should read the proof. Okay, right? Okay, fine. But here I will discuss on this later, but probably you can ask the TA why I am saying recommending read the proof of this theorem. Theorem of page 107. Okay, look. A implies B and B implies A. A implies B already you have used in the proof. But B implies A here is a separate proof. That B implies A. This is very important. Here two things. Basically, it is important for two things. For the trick, here I am proving by contradiction. Okay, like let me tell you that how. So you should look at what I am proving. Look, when suppose what I am doing, if suppose if possible, suppose f is not continuous, at x. Suppose f is not continuous at x. But you have this condition B. That means whenever xn goes to x, implies fxn goes to fx. समझ गए आप? Now, if you have f is not continuous, contradiction in the logic term is contrapositive. If f is not continuous at x means what? That means, look, if is continuous at x, that means given epsilon greater than 0, there exists a delta greater than 0 following this. Given epsilon, that means for every epsilon greater than 0, you will get a delta. For every epsilon. For every epsilon greater than 0, there exists delta greater than 0. Delta depends on satisfying those conditions. Now, if I say not, that means for at least one epsilon it fails, right? For at least one epsilon. So if it is not, that means there exists epsilon greater than 0 for which it fails. That means what? For which no such delta, for which no such delta works. Right? You'll have to understand the contradiction that if you negation, you are assuming the negation of the statement. You'll have to understand the meaning of the negation of the statement for which no such delta works. So particularly delta equal to 1 by n won't to work. Won't to work. That's a technique. Look, I have seen. So it won't work. Okay. That means what will happen? That means you will get xn for this, you will get at least now for this delta doesn't work. Okay. Okay, so that particularly this doesn't work. This doesn't work means what? That means you will get one such point that you are calling xn. There exists xn such that you have this part. You have rho fx fxn but rho fx fxn, there exists epsilon greater than equal to epsilon. This will mean, but look, for each n you are getting this. That means you are getting a sequence xn, and since this is less than 1 by n, that is the trick. That means xn goes to x because of this. But this is always distance between fx and fxn greater than equal to epsilon. And obviously fxn doesn't go to fx. Okay, right? That I have given the proof that. So we were getting a contradiction. That means A is not satisfied. I have proved basically if B is not satisfied, then A is not satisfied. So that B must implies A. Now look, make sure that you read the proof of B implies C. But here, I am saying you are using axiom of choice. You are using B implies C. But how? First of all, how? And then how will apply? Look here, for each n I am picking up a sequence xn point. I am picking up a point. So if you just don't apply anything, that means you are picking up process will be infinite. For each n you are picking up a point xn. Okay, so that you are not allowed. This will be indefinite process. That means you need to use some action. So actually you are using action of choice. But point is that how will you use action of choice? So particularly action of choice application, I told you that easiest way to see, find out, you have a collection of bags. Basically infinite collection of bags, and from each bag you are choosing a point. Okay, to make your own bag. Now the point is that what will be those bags here? That you should think about. Okay, right? Now look here, I have given the meaning of that sequential characterization of continuity. That xn goes to implies fxn goes to fx. That means, let's look here. When if f is continuous at x, that means if f is continuous at x, that means you are getting what? In the this is the notation I told you. In notation you are getting this. Look, this limit, that is inside. So you have two operations, limit and f. You can interchange here limit and f, here f and limit. Okay, so that is the importance of the continuity, actually biggest importance, that you can interchange limit and f. Okay, right. Okay. I think I told you I will take another half an hour. So I am giving you 5 minutes break. I will come back. Okay. Okay. After 5 minutes, I will come back. I will start again. Okay.
Okay, sir.
Okay, sir.
Hello? Hello? Hello?
Yes, sir.
I'm going to
Yes,
start.
sir.
Yes, sir.
Okay, look at now uniform continuity. This is very important thing in metric space. Okay, what does it mean, the uniform continuity? That look, the word uniform continuity. Look, not only continuity, here you have the adjective uniform. Okay, but that means what? So look, given epsilon, we are choosing delta. But look, in this definition, I have doing that f is continuous at x. I was giving the definition, f is continuous at x at a given point. So that after at x that you have fixed, and then you are doing it. So that there exists delta greater than 0. I said delta depends on epsilon. So actually delta depends on not only epsilon, also on x. So this is a function of epsilon and x as well as. Okay, function of two things, epsilon and x. I have given you examples, on the 5 examples. You can pick up the example, see that where it depends on x. Okay, you can see that. Look, sometimes when you have just delta equal to epsilon, you can choose some examples. That means it doesn't depend on x. That means same delta will work for all x. Same delta. Okay, but another place you will see that delta will depend on x. Okay, like if you take this function, simple function, f r 2r x to x square. It's a nice function. This is continuous. Here you can see that given epsilon, you take 2 points, 0 and 1. You see that given epsilon, same epsilon, the delta will depend on, you will have to choose different delta actually. Not the same delta will work. Okay. That you can see that. You can take epsilon, take epsilon equal to 1. And then pick up these 2 points. See which delta you will get here. Okay. Right. You should think about it. That means here delta not only depend on epsilon, delta will depend on x also. But some other when you have delta equal to epsilon, the identity function, then you can have the same delta. And same delta means uniformly you can choose same delta. That's why the uniform comes. That means same delta. Basically, same delta independent of x. That means if you have independent of x, okay, right? So that means since it doesn't depend on this, look, here I have given the definition on that, so I don't need to choose x. Now all I say that f xd y rho. Now look, uniform continuity first of all doesn't make sense to talk about uniform continuity at a point, because look, I'm talking about delta as a function epsilon and x, and I'm saying it is independent of x. That means when you're talking about uniform continuity, it has to be the whole thing, not at a point. Okay, otherwise it doesn't make sense. My problem, because I'm saying it is independent of x. So uniform continuity is the whole set. So it's a global concept. It's a global concept. That means given epsilon greater than 0, there exists delta greater than 0. Here you should write delta depends on epsilon only, such that here. So as long as the distance between, I have not chosen x and x prime, but whenever you have this, you have this. Look, where x prime belongs to x. As long as you have this, then you have this. Okay. Got it? Make sure that you understand that this delta only depends on epsilon. Okay. Right. Now look here. I was just giving an example that you should check that. This is not uniformly continuous, but to restrict the domain to a bounded subset, same function. So I told you the domain, it also depends. Suppose you take this. The bounded set you are taking, the closed bounded interval. You can take open interval, doesn't matter. If you take the here, it is uniformly continuous. You just need simple calculation, 2-3 lines. You should, this is BSc knowledge, it should be, but here it is not uniformly continuous. Reason is, I can tell you that why it helps here. Look here, when you have this, let me tell you that. Just see that. Oh, okay, let me look that where f a b to r square. Why it will be uniformly continuous? Well, look, if you take fx minus fx prime equal to x square minus x prime square, okay, this equal to what? X ठीक है, समझ गया ना? But look, this is but x, this thing, it will be what? Because these are bounded on that, right? So there exists m greater than 0 such that for all x belongs to this. So this is will be actually this. So given epsilon greater than 0, there exists delta. What will be delta you take? You take delta equal to epsilon by 4m. समझ गया? That will work. Got it? Hello? You are listening to me?
Yes, sir.
Yes, sir.
You are understanding what I'm doing?
Yes,
To
sir.
take, look, if this is
Yes,
x
sir.
minus x prime less than delta, that means it will be okay. I could choose epsilon by 2m.
Epsilon by 2m. Yes.
That would have worked also, but just for the better thing I do that, so-called better thing. Okay. Now look at it works. But if the same function, look what I have used. This is bounded. I have used this thing. But here you won't get this thing. If you have the same function, sorry, this is not r square. Here r. This won't be uniformly continuous because I won't have this choice. Got the point? Okay. I mean, if you can assume that is uniformly continuous, you can have a contradiction. But later on, when I give the characterization, you can easily prove that. Okay, so that, look, that it depends on the domain also, the uniform continuity. I'm saying whenever a function, just you don't go by the formula of the function. It depends on the domain and the range. Okay, right? Well, so that here the definition. Now look, sequential characterization of uniform continuity. Sequential characterization of continuity, what I am giving you, obviously you won't find in the Ali Francis Perkins book. Very likely you won't find in any book. Okay, that sequential characterization of continuity I'm giving here. Okay, that, but it is very simple characterization. But well, I'm coming to the point on that here, instead of because of sequential characterization of continuity, I need to give you the definition of asymptotic sequence. This is a pair of sequences, like asymptotic curve. Look, this two are asymptotic, right? Okay. Similarly, you can define asymptotic sequences. Suppose you have a metric space, you have two sequences here. Since I am only one metric space, I can take one. So I will say this is asymptotic. That means if you have this, this is a real sequence. That means given epsilon greater than 0, there exists an epsilon. It will depend on epsilon. That exists such that dxn yn less than epsilon for all n greater than equal to n epsilon. It's called asymptotic sequence. Okay, right? Of course, if they are same sequence, that will be true. But simple example, you can see that that
1 upon n upon 2n.
You take xn equal to 1 upon n and yn equal to 1 by 2n. Okay, so that you can do, or else you can do this simply this. Look, I can do something. Those are actually converging sequence. I can take xn equal to n, yn equal to n plus 1 by n. समझ गया? Look, they are not converging, but they are asymptotic sequences. Okay, so asymptotic sequence is only different per pair of sequence. So we use a notation this, like that means they are gradually getting close to each other. This is a notation for this. Okay, this is called the asymptotic sequences. Okay, right? Now, this is definition of asymptotic sequences. Okay, like example 1, I have given that. Okay, now the thing is that I have given an exercise. Can you find a pair of asymptotic sequences in BXD where X is a non-empty set? Now I have given a result that is very simple that to prove. Sorry. Suppose you have a metric space and you have a pair of asymptotic sequences. And actually asymptotic sequences they behave nicely in a sense, they behave like actual twins. They behave like twins. Suppose this is Cauchy. If one of them is Cauchy, that means then it has to be Cauchy. Has to be Cauchy also. If it is converges, it will have to be convergent. Okay, that I put an exercise. Okay. Now the thing is that what is the sequential characterization of uniform continuity I have given? I have given this. Suppose you have this, then the following are equivalent. F is uniformly continuous, short thing. U for uniformity, and this is for C dot. Uniformly continuous. B, I'm just writing informally. F sends every pair of asymptotic sequences to a pair of asymptotic sequences. Okay, that means image of a asymptotic sequence again will be a pair of asymptotic sequence again will be asymptotic. So if it is not asymptotic, then it is not uniformly continuous. The proof, look, that's why I was giving the proof, the sequential characterization. Here, A implies B is B implies A. You see that again you will be of course using the exam of choice, but the proof is similar to what when I was giving the sequential characterization of continuity. You should look that. Okay, right? Otherwise, next time I will discuss on that. But the same proof, basically same technique rather, same technique will work. Okay, right? So that you should look at that. What is the theorem number I have given? I have given any theorem. Theorem statement, page 109 and 10. Okay, so look at B implies A again. That if you are using negation, if the negation, you should know it. Thing is that when you are using negation, you'll have to understand precisely the meaning of the negation. Understand? Okay, right? That I'm using it. Now the thing is that right now, so you should read the proof. Okay. If you do not understand, you can ask me, you can ask Bhavna. Okay. Now look at the example that this thing. I said this is not uniformly continuous. Okay, you can use the definition of uniform continuity to prove it. It's not difficult, but still it will be a little bit messy. But if I use this result, now look, just now I was doing it, that xn equal to 1 by n and x prime n equal to take n plus 1 by n. Okay. Now look, xn, this is asymptotic. Okay. But if you take the square, look, xn square minus x prime n square. Okay. This will be how much it will come. 1 by n square will be cancelled on that. Okay. Plus 1 by n. Oh, this is n. Sorry, this I made a mistake. That's why I was wondering. Okay. So this is n square and minus 2. Okay, so this goes to 2. समझ गया? That means xn square, this sequence is not asymptotic. Got it? So asymptotic sequence is not going to asymptotic sequence. So it is not uniformly continuous. So look, simple application of this, how we can use this fact. Okay, right? So today I won't teach you anything more. Just I want to tell you that. Okay, something best. But the thing is, so this good example you should look here. Now the thing is, when you check that, suppose you have a function, you have to take closed and bounded. You take a continuous function. Suppose continuous function. It can be shown if you take domain. It will be always uniformly continuous. It can be theoretically proved. But if it is not closed, a continuous function need not be uniformly continuous. The example is, look here. This is continuous, not uniformly continuous. Why it is not uniformly continuous? You can check that uniformly continuous will always send Cauchy sequences to Cauchy sequences. Look, continuous map sends convergent sequence to convergent sequences. Uniformly continuous sends Cauchy sequences to Cauchy sequences. That is the image of a Cauchy sequence to Cauchy sequence. समझ गया? Though convergence may not be true, the uniformly continuous map will always send Cauchy sequences to Cauchy sequences. Okay, but here look, why it is not so that if you use this result, look here 1 by n, it is here, it's Cauchy here, but its image is n, which is not Cauchy. So this is not uniformly continuous, not uniformly continuous. Okay. Again, but here everything, a continuous function will be uniformly continuous, but this is sufficient condition that, okay, if you have closed bounded interval, it is not necessary condition. Now that means a continuous function is if it is uniformly continuous or not. Every continuous function, one continuous function may be uniformly continuous. Suppose you say every continuous function. Suppose now the question basically you ask this, that suppose you have this metric space. Every continuous f, this is a question. Continuous f, every continuous f, is every continuous f uniformly continuous? Okay, is every continuous f uniformly continuous? It depends on the domain. Okay, now suppose it is true, some for xt, then xt is, if it is true, y rho I can take real values if you want. Okay, if it is true, then xt is called an UC space, U uniformly, or Atsugi space. Here I should tell you something history of that. Actually, now the people prefer to use UC space because this Japanese proposition, 1958, in Pacific Journal of Mathematics. It's a very good journal. He actually studied in detail that, but before that it was studied also. But people didn't pay much attention. When it came like a good journal on that, then people looked at this very carefully on that. And that is why some people started calling it Atsugi space. Okay, here, that I told you this can be replaced by any this real metric space. That definition 23. Okay, right. So this is called Atsugi space. So I have given a characterization of UC space and that here, that I will do in result on the page 113. That tomorrow I'll do it, but here I just would like to say, you go to the net, search on this, search on that. UC space, Atsugi space. Look, these are actually is a course on real analysis, but today actually analysis, real analysis course, the graduate level, US graduate level means postgraduate level. It means actually analysis on metric space. So this is all part of analysis on metric space actually. Okay, so if you go to search on the net, UC space or Atsugi space, okay, you'll be surprised to see that which people did what. Okay, so it's an interesting question. What I am saying, I am today asking that, look, you should rate continuity of course very well, but then you should rate uniformly continuous well. First thing you should understand, if you do not understand continuity and uniform continuity well, you won't be able to understand metric space enough, well enough. Okay, so that it is very important that you understand continuity, uniform continuity. Okay, tomorrow at the same time I will take the class 1 hour and a half. Okay, I don't know. I sent the invitation, but my laptop was not showing it. Okay, so I will meet you tomorrow. Look at this. Okay, okay, bye.
Okay, thank you, sir.
Thank you, sir.
How did you do in the exam? Huh? I'm asking you.
Our batch, sir.
How did you do in the exam?
Our batch, sir.
Have you got the papers yet? Not. Huh?
Sir, what, sir?
I'll have to talk to Bhavna. Okay. Okay. To see you tomorrow.